take a look. Okay, who else finished it? All right, nitrates what? NO3 minus. Is there oxate? Is that fluorate? There is that. FO3 minus. Phosphate?
PO4
PO4 3 minus. Sulfate?
Support
Chlorate?
CO
Okay, do you see any kind of pattern here?
they all incorporate oxygen.
They all incorporate oxygen. Most eights do. There are a few eights that don't, but most eights are oxyanions. That's good. Okay, that's one of the patterns. What else? Do you see a pattern based on the number of oxygens? Can you see a pattern based on the number of oxygens?
Has to do with the valence.
Yeah, it has to do with the valence. Or maybe it doesn't, because did the number of oxygens change here? Or chlorate? Chlorate's this. Do you know what iodate is?
Oh, it's IO3.
IO3 minus. Bromate? BrO3 minus, etc. Actually, chlorine, bromine, iodine, sorry. But as we go along, we see, okay, the pattern is this. We have this kind of L shape here, and all these have three oxygens. All right, when we look at these have 4 oxygens. All right, do you notice that, oops, I need to make room here, sorry. We're going to make a little bit of room here, but just write this, 4 oxygens. All right, so now there's a pattern here, right? It's not just rote memorization, but we see, okay, these guys have 3 oxygens, these have 4 oxygens. Do you see a pattern in the charge? Yeah, we see a pattern in the charge. It goes 2, 1, and then it stays at 1. This goes 3, 2. But the number of oxygens changes here. So we have an inner block and an outer block, right? All right, so what scientists are always looking for, they're looking for patterns and trends. Sometimes it helps to graph things, sometimes not. In this case, we wouldn't graph, but scientists love to do graphs because it sometimes shows a correlation or some kind of pattern or trend that we can follow. Now, the charges go like this. So what we can do is we can make predictions based on patterns. We might call this a law. Maybe it's too early to call this a law, but let's try to make a prediction, right? And one of our predictions will be like this. I don't have any other colors here. All right, this is going to be a prediction. What is arsenate? What would you guess arsenate is? This might be a hard prediction. Let's start off with an easier prediction. What do you think borate is? The borate ion. Give me the formula for borate. BO3? That's what I would guess, BO3. Now the charge, what would you guess the charge?
3 minus.
3 minus. And that's correct. That is the formula for borate. And so all we did was we just used a pattern to make a prediction, or just like you would use a law to make a prediction, but I don't think we could call this a law just yet, right? A law, it has to be at least more observations associated with it, probably. Okay, what's before phosphorus and under carbon? Silicon. Okay, so what do you think silicate ion is? Let's make a prediction about silicate.
So 4 minus.
Well, SiO4, 4 minus. You know what? That's correct. SiO4, 4 minus is the formula for silicate. And so based on these observations, we're able to make predictions versus rote memorization. If you were just to memorize things, could you ever make a prediction? And so some people, we often get complaints in science. This test is nothing like the homework, nothing like what you talked about in class, is because their level of understanding was at the rote memorization. If you just memorize these using flashcards, you'd never be able to predict, right? This kind of stuff. And so this is what you're going to see, you know, as you continue on in science, is you got to understand it to a little bit deeper level than just the first step of the scientific method, which is just raw observations. You know, and so getting from raw observations to patterns and trends is a huge part of science. Getting from there to there is called data reduction. You just take a whole bunch of this data, which is just like, I got to memorize 30 ions, right? You reduce that down into some patterns, and then it's a lot easier to deal. And so this is one of the ways we deal. One of the ways we deal is we start off, in science is a two-pronged approach. Science is, you have there are a lot of people who want to do science as a one-pronged approach, right? They say, you know, nowadays we don't need to memorize anything. When I hear that, it makes me cringe because, you know, if you don't memorize anything, you're never going to see any patterns, you know, or at least understand these things. And so in science, there is quite a bit of memorization there. You got to memorize stuff. You can't always look things up, right? Sometimes it's just not there, especially with new observations. And so the two-pronged approach is, you know, there's some factual knowledge, you know, some basic knowledge that you need to memorize and understand. But obviously, we would like to predict these things using theory. You know, what's the theory underlying chemistry? What's that theory called that underlies chemistry? Well, you know, the chemistry, the theory that forms the basis of our understanding of matter and how it works, you know, is called earlier I mentioned it. Just take a guess. There's no penalty for guessing. Yeah, quantum mechanics. And so a lot of people say, you know, there's no need to memorize. Well, okay, if there's no need to memorize, just tell me, predict this using quantum theory, quantum mechanics. Can you do it? Is quantum mechanics easy theory to use and apply? No. And so, you know, the same thing goes. You know, there's so many variables in experiments. You know, you could do a chemical reaction under a whole set of conditions like temperature, pressure, concentration. Those are going to alter how those behave. You know, are you going to predict those quantum mechanically? Yeah, you know, it would be great to do that because you wouldn't have to do the experiment. But, you know, we're not quite at that level to do that, and the calculations get horrendous. You know, quantum mechanical calculations are difficult to solve. In fact, the Schrodinger equation, you guys remember the Schrodinger equation? The Schrodinger equation can only be solved exactly. The Schrodinger equation gives us our orbitals, right? It can only be solved exactly for the hydrogen atom. If we go to the helium atom, you have to use approximation methods to solve the math. You know, guess. You know, it's kind of guessing, but it's better than that. But anyway, so, you know, to get a really good understanding of chemistry, you have to have a lot of factual knowledge. You got to understand a lot of facts of nature in order to do that. Okay, that's one prong. You know, we just understand the facts, we see patterns, we see lots of patterns, we can make predictions. And so that's how we're going to handle the chemical reaction, you know, and see, oh, there's certain patterns in the way, you know, matter reacts. And we're going to use those patterns to make predictions, just like we did here, you know. What would be great, though, is to be able to use quantum mechanics and predict everything. You know, I'm going to use quantum mechanics and predict what's going to happen, what my products are going to be, or whatever. You know, but it gets complicated. Well, anyway, so here we are. This one might be tricky unless you already know it, but what is arsenate?
AS05.
Yeah, you would think ASO5, but you know, it turns out it is ASO4. Yep. ASO4 3 minus. What is a selenate? So you're going to have two types of people. you're going to have the type of people who will know sulfate, phosphate, all these others, and then you'll have who won't know anything about arsenate, selenate, borate, silicate, and then you'll have others that can answer what this is. What do you think selenate is?
SeO4.
And that's correct, SeO4 2-, right? And so this is pattern, but we just don't want pattern. Maybe we can call this a law, the law of the periodic table or something like that, right? But we want to understand this at a more fundamental level. Is this really understanding it at a more fundamental level? No. And so the fundamental level is, the description of why this pattern exists. And so what would your hypothesis be, your hypothesis regarding this?
Electron orbital theory.
Yeah, it's got to have to do with orbitals, right? Orbitals. And you might hypothesize that these you cannot expand the octet, these you can expand the octet, et cetera, et cetera. So we can get into it from there. But a lot of the stuff we don't get into it. A lot of the stuff we just, based on our empirical observations, this is what we're going to predict. And a lot of science is still done this way. People are trying to find the best catalyst, for converting, let's say, water into hydrogen gas. What's the best catalyst? And a lot of that is just mix, make, and check, Mix, make, and check. And so they tried a whole bunch of different formulations. And so they have these little mini reactors. They can do 1,000 reactions on a small plate and then make 1,000 formulations, just slightly varying one ingredient or one component, one reactant, we call it, right? And then check each one to see which ones works best. Whereas it would be great if we could just use theory, quantum mechanics, and predict which one's best. That way we wouldn't have to buy 1,000 reaction plate. We could just buy one reaction plate, save a lot of money. Right? But it's not quite at that level where it's so easy to predict things quantum mechanically. All right, so getting some. Well, go ahead. The thing is, the best thing to memorize, and this is a pattern I always give in Chem 1A, but a lot of people don't remember or don't, don't really care about this pattern. And so the best thing, and this is what I want you to do on your paper, is just to summarize it in your own words. What is the pattern, so that you can remember it. Because the best thing to do is not to memorize somebody else's words, but it is to write your own words. And so this is what I always did with the lecture notes. With the lecture notes, I always annotated them and summarized, this whole section's about this, and these are the key points, and this. And so when it came to study for the final, it made things a lot easier because everything was in my words. My understanding of this is this, that kind of thing. And so, so from Chem 1A, did you memorize how many types of chemical reactions there are? Or did you come up with, my understanding is that this many types of chemical reactions, right? And so, chemical reactions, are chemical properties, right? So this is why my PowerPoints are called chemical properties. Chemical properties or reaction. Okay, the first question I'm going to ask you is how many types of chemical reactions are there that you learned in Chem 4, Chem 1A? Okay, how many types of reactions? Can you recall the, what were some of them? Maybe name some just to spark it. Acid base, okay, that's one. Okay, gas decomposition, or decomposition to form a gas or something? Okay. Thermal, okay. Redox. Single, double. Maybe you don't have a number because there might be like an infinite number of reactions that can potentially occur, right? But that's like the rote memorization. You memorize each individual reaction. Do you want to memorize each individual reaction, or do you want to see some kind of pattern to this so we can make predictions based on these patterns? What do you want to do? You want to memorize thousands and thousands of reactions? This is what some people do in organic chemistry. They just memorize, hundreds of reactions. memorize. People with photographic memories, it's okay, but most other people are going to try to come up with some kind of pattern to see how things react so they can make predictions. And so as far as patterns of reaction, how many major types of patterns are there that you encountered in Chem 4 or Chem 1A? If you were to summarize, looking back, this is something that you need to start doing, as you progress in science. What you need to start doing is you just don't leave it at carbonate, nitrate, sulfate. What you have to do is when you go through your notes, this is the advantage of going through. When you go through week 1, like 10 times, 15 times, then obviously the patterns start to stick out, right? And then you start to notice things that you might not have noticed before. And so this is why the stress level, versus, I'm going to just review that the week before the final. The week before the final, your brain doesn't have enough time to make those connections, see the patterns, right? And so this is the huge advantage to studying, this kind of method that I found. Obviously, everybody has their own study techniques, but if you're reviewing your Chem 1A chemical reactions and you've read it, probably in Chem 1A, how many pages of notes did you have for your chemical reactions? What did you say? Acid, base, redox, whatever else. How many pages of notes? Chem 4, Chem 1A? 50? 10? 50? Half a notebook? A full notebook? Well, if you go through that, a full notebook, that's kind of a lot of stuff, right? Then to review a full notebook or half a notebook or 50 pages or 10 pages or 5 pages, some people have 0 pages because they don't take any notes. That's totally unheard of. The taking 0 notes at UCLA, I didn't meet one student who never took any notes. Well, actually, maybe I did, because at UCLA they sell lecture notes. I heard that they were selling one course, lecture notes, for $340. People are buying it up, right? It's actually an audio plus video type deal. $340. So lecture notes is a big business at UCLA, and those lecture notes are actually quite good because the note taker is a professional note taker, and they go to the professor and make sure everything's accurate in there. Lots of stuff is copied down inaccurately. But the thing is, you got that many pages, and for the whole semester, how many pages of notes do you have? A lot, right? Or whatever, or pages of the book. Some people, they don't like to take notes, they like to read from the book. Well, how many pages of the book do you have? 500? 1,000? Right? Whatever. How are you going to get that information? You get that information by, repeatedly going through it, and then looking for patterns, and then trying to summarize that. So if I were, with my new study techniques, going through chemical reactions, I wouldn't be just going carbonate, sulfate, memorization. I would be going, there's an interesting pattern here in this, and I see that this chemical reaction is similar to this, but this one's not similar to that, right? I would see that because I've gone through it so many times. And so think about how many people do not do that. And so if you're one of the few people that do that, then you're going to have a huge advantage, aren't you, in the class? Well, anyway, so how many types? Well, I've gone through it so many times, and this is not mine. Other people have gone through it so many times that there are going to be 3 major types of chemical reactions. One is like double replacement, but it's different than a little different than double. We call it metathesis. You just write it down. 2 is let's say acid base, and 3 would be redox. And so all those reactions that you encounter can be fit into one of these 3 categories. And metathesis, we'll talk more about that next time, but we're out of time, I think. What time do we go till? 55? Yeah. All right, we're out of time, so we'll have to cover that tomorrow. So take a look at the power